This video is about rational equations. We're going to start by recalling a topic we've done previously, which is solving a linear equation that happens to involve some fractions. So consider the following example. We have 5 plus a fractional term where the numerator is x minus 2 and the denominator is 3, and then equals, and then another fractional term where the numerator is x plus 3 and the denominator is 8. In a case like this, which again we've done in the past, we used a method called clearing the fractions. And so to remind you of how that worked, we'd have to find the least common denominator first. So for 3 and 8, of course, that would be 24. And then to clear the fractions, we would take that LCD and multiply it by every term on both sides of the original equation. So with the 5 as the first term, we would multiply that by 24. Even if it's not a fraction like 5, we'd still multiply all the way through. In the second term, we had an x minus 2 all over 3. And we're putting all these original terms here in parentheses and then multiplying the 24 LCD next to them each time. So same thing on the right side of the equation here. We have x plus 3 over 8 in parentheses and then a 24 being multiplied by it. And then the whole point of clearing the fractions, as you recall, would be to reduce the fractions, which will then eliminate all these denominators. So we have here, if we go across 24 times 5, now that's just 120, there's nothing to reduce with it. But moving on to the next term, when we have the 24 over the 3, we could divide those each by 3, and that would give us really an 8 instead of the 24 and a 1 instead of the 23. So in result, we would have 8, and then in parentheses following that, we would still have the x minus 2 from that numerator that wouldn't have been reduced. And then we continue the same kind of thing on the other side of the parentheses. We would reduce 24 and 8 by dividing those each by 8. 24 divided by 8 is 3. 8 divided by 8 is 1. And then we rewrite this with a 3 outside in front of the x plus 3, the numerator, which would still be there. And then at this point, of course, we would find a much simpler looking problem and then solve using all of our basic algebraic steps. So in the scope of this example, I'm not going to go ahead and finish this, but it would be finished using the simple algebraic steps that we've done already. So finish that and you'll find an answer for x. Now, that's a review on what we've already done. Now, what we're going to do is maybe borrow from what we just did, but then extend it a little bit more. So we're going to solve an equation, but this time the equation looks as follows. It's 5 minus a fractional term where it's 2 in the numerator and then x minus 5 in the denominator equals, and then another fractional term on the other side where 3 is in the numerator and then x minus 5 is in the denominator there as well. Well, this time, notice the difference between this example and the one we just did to warm up here. You'll notice they actually look fairly similar in their structure. However, what we're seeing in this equation is that in the fractional terms, the denominators have variables as parts of their expression. So we have an x minus 5 in the denominators as opposed to just the numerical denominators in that previous example to warm up. So that's the difference between what we did and what we're now doing. It's somewhat similar, but yet different because of that. We're going to try the same method to solve this equation. That is, we're going to clear the fractions, which means we still need an LCD. Now, this time the LCD would happen to be x minus 5. And so we're going to multiply through all the terms by that LCD, just like we did in the previous problem. So we'll have 5, which was the original first term, and we're going to multiply that by x minus 5. And then we continue on the same way. So we have an x minus 5 times that next original term, which was the 2 over x minus 5. And then on to the right side, same thing. We're multiplying the LCD of x minus 5 times the original term of 3 over x minus 5. And at this point, we do what we did in the previous problem, which is multiply through to simplify. So on the left first term, we would distribute this 5 into both of those terms of the LCDs to get 5x minus 25. In the second term, notice we have this x minus 5 over x minus 5. Well, those would match and cancel, which makes us happy because then all that's left is a minus 2 for that term. If we continue on to the right side of the equation, we'll notice a similar scenario where the x minus 5s cancel, and that leaves us with just a 3, which was that original numerator over there. So you can see it drastically got simpler after clearing the fractions, and all that's left would be a 5x minus 27 equals 3, and then we would add 27 to both sides to get 5x equals 30, which would mean x equals 6. Now, that's the way of solving an equation by clearing fractions. As mentioned in that previous example, we've already done that. But what's different now with a rational equation is that you'll see not only fractions, but fractions where the denominator involves some variables. It's handled the same way by clearing the fractions as shown now, but there's an additional new step involved. So I'm going to make a note of this right here. There is a new step. And that is we have to check for what are called extraneous, E-X-T-R-A-N-E-O-U-S, extraneous solutions. Okay, now to check for extraneous solutions, all we have to do is plug our answer, what we think is our answer, back into the original problem to see if it actually works. So we'll be checking 6 by plugging it back in. So is 5 minus 2 over 6 minus 5 equal to, I'm going to put a question mark above the equation because we have to make sure it actually works. Is that equal to 3 over 6 minus 5? And so as you can see, we're simply plugging the answer we think we have back into the original equation. Of course, this would mean 5 minus, this is really 2 over 1, so it was 5 minus 2 equal to 3 over 1, which is really 3. 5 minus 2 equals 3. Yeah, that actually works fine, which means we say, yep, x equals 6 is our solution. It worked out fine. So in the checking step, it's important to note that sometimes the answer we got is fine. It actually checks out, but sometimes it doesn't. And we'll see examples of that coming. But if we don't check it, we'll never know. So that's a new step in solving an equation if it's a rational equation like this. Okay, let's try another example. This one begins with a couple rational terms on the left side. The first one is 1 in the numerator and x minus 2 in the denominator. Then we say plus, and then the next fractional term is 1 in the numerator and x plus 2 in the denominator. And then that's equal to, on the right side, we have 4 over x squared minus 4. Now, to clear the fractions, as we've seen above, we need to find the LCD of all these fractional terms. But as you recall from finding an LCD with rational expressions, as we've done in previous topics, that involves factoring any denominators first. So you'll notice the right side denominator, the x squared minus 4, that's a difference of 2 squares. So we should actually factor that first. That would be an x plus 2 times an x minus 2. Once you factor the denominators, then you'll look through and combine any factors you see of any denominators on either side. We want the highest power of any of those. So I see an x minus 2 as that first denominator factor. Notice there's no other higher power of it. There's another x minus 2 at the end, but it's also a single x minus 2. So we're going to use that single x minus 2 as the highest power representative of all those x minus 2 factors. Moving on, so we can, I guess if you recall how we did this before, you would check off all the x minus 2's. But then we go on and say, well, there's an x plus 2 as well, but in the same way, we have a single one and a single one, which means a single x plus 2 is the highest power we see. We have to use it as the representative factor then. So our LCD is a combination, a product of x minus 2 and x plus 2. Now, once you find the LCD, in order to clear the fractions, we're going to multiply it by all the original terms. So this step gets fairly ugly because of how much there is to write out, but then usually it gets way cleaner directly after it. So I'm going to write out the LCD of x minus 2 times x plus 2, and then multiply it by all these original terms in parentheses. So we had 1 over x minus 2 as that first fractional term. Then we had a plus, and we keep going. We copy the LCD yet again, so x minus 2 times x plus 2 times that next original term of 1 over x plus 2 in parentheses, and then the equal sign, and then one more time here, x minus 2 times x plus 2, the LCD, and then that last original term was 4 over. Now, I'm going to put the factored version of that original denominator there on the right side. Instead of x squared minus 4, we already had that factored as x plus 2 times x minus 2. It's just going to be easier to see it in that factored form for when we reduce these. So I'm going to write it that way. Then, as we've seen in this process of clearing the fractions, we go back through and cancel things that match. So notice in the first term all the way to the left, we have an x minus 2 on top and an x minus 2 down below. Those would match and cancel, which would leave behind the x plus 2 factor we had times the 1 in that original numerator, which of course is just x plus 2. Then we move on to the next term and do the same thing. We have an x plus 2 in the numerator and x plus 2 in the denominator. Those would match and cancel, and that would leave us with an x minus 2 times a 1 up there similarly. So that would be just a plus, keep that middle sign just brought straight down, and then an x minus 2 times 1 is just an x minus 2. Then we have our equal sign. On the right side of it, we have some more canceling to do. We have an x minus 2 that will cancel, and we have an x plus 2 that will cancel. And so those are all cancel, leaving us only with the 4 in that original numerator. So x plus 2 plus x minus 2 equals 4 is how the equation looks after clearing the fractions. Notice I promised it would get much simpler, and obviously that did. So now we'll just combine like terms to get 2x, and then the plus 2 and the minus 2 would just cancel. So we have 2x on the left side equals 4 on the right side, but then 2x equals 4 if you divide by 2 on both sides would mean x equals 2. Okay, well, let's not forget, it can be exciting to get our answer, but we must check now that we're dealing with these rational equations, and we know that. To check, I'm going to plug my answer of 2 back in the original equation. So go back and find it. That would be 1 over 2 minus 2 plus 1 over 2 plus 2 equals with a question mark. We're still investigating this. And then 4 over, and then if I plug in 2 for x squared, I'd have 4 and then minus 4. So now we have our equation to check, but you can start to spot how you might get a problem in some of these cases. Notice the first denominator of 2 minus 2, that would turn into 1 over 0, plus the second fraction would be 1 over 4, equals, and on the right side we'd also have 4 over 0, but that's a problem. We know we cannot divide by 0, as we would be trying to do in that first and last fraction. So we have to say that this is a problem. I'll just make a note, cannot divide by 0. We've seen that before, and we know we're not allowed to handle that. So what that means is we have to mark this solution that we got, or we thought we got here, x equals 2. We're going to have to mark that as extraneous. Now, because of that, when you mark something as extraneous, it means it doesn't actually count as a solution. So if the only one that we got, x equals 2, is extraneous because of this check causing division by 0, then that would mean it actually is not a solution, which means the technical answer to this problem is that there is no solution because the one we got is extraneous. So we'd actually officially answer no solution to this problem after all that work, finding out that, oh, the one we thought we had doesn't actually work. Let's go ahead and try another example. This one begins with a couple rational terms involved in this equation. The first one has a 4 in the numerator. The denominator is x squared plus 3x minus 10. Then we have a minus sign, and then another fractional or rational term, which is a 1 in the numerator, and then x squared plus x minus 6 in the denominator, and then equals. And then on the right side, we have 3 in the numerator, and then x squared minus x minus 12 in the denominator. Well, as you've been seeing so far, we have to clear the fractions in order to solve a rational equation like this. But in order to clear the fractions, we need an LCD. But in order to get an LCD, we would have to factor all of these denominators. So we have to bring back all of our factoring skills. I'm just going to go through these quickly here. The first one, the x squared plus 3x minus 10, that would turn into an x plus 5 times an x minus 2. And so again, there are various methods for factoring. We've done all those and reviewed them recently, so you can go back and pick your favorite one to use to factor these trinomials. The second denominator would be factored into an x plus 3 and then an x minus 2. And then the last one on the right side would also be factored into an x minus 4 and then an x plus 3. Now, in order to find an LCD, we have to go through all of these factors and pick the highest powers of any unique factor of any denominator. So you go left to right, perhaps, and say, well, the first one is this x plus 5. I don't see another x plus 5 factor anywhere, which means there's no other higher power of it than just a single x plus 5, but we have to use it to represent itself, so we'll use it and check it off. Moving on, we see an x minus 2 next. Notice there's another x minus 2 in that second denominator, but it's not a higher power. It's not a squared or cubed power of that x minus 2 factor. So we'll use a single one, x minus 2, as the highest power representative, which would represent both of those x minus 2s, so check them both off. Then we move on to the x plus 3. We see in that second denominator, notice there's another x plus 3 at the end, but again, they're both single x plus 3 to the first powers, which means we're going to use a single one to represent both of those. And lastly, there's an x minus 4 that didn't get checked off yet. Obviously, it's the only one around, so we're going to use it to represent itself. X minus 4, it's a single power of that factor. Okay, so our LCD has 4 binomial factors, which is kind of crazy. And because of that, sometimes rewriting the next step by copying down this 4 binomial LCD with each of these original fractional or rational terms can get a little crazy or ugly or just take up too much space. So instead of actually writing it out all again, I'm going to skip the write out step and just go through and understand what would happen. Because remember, when we multiply this LCD by, let's just say, this first original fractional term, anything in the denominator factors that would match in this LCD would cancel and therefore disappear. Well, that would leave the 4 in that numerator that we had, and any factor from the LCD that wouldn't cancel with this denominator. So notice that would leave behind the x plus 3, because that wouldn't cancel with the denominator, but it would also leave behind the x minus 4, because that wouldn't cancel with anything in that denominator. So we have now, as our first term, our new first term here, 4, and then times x plus 3 in parentheses, and then x minus 4 in parentheses. Then we move on and do the same thing to the next big fractional term, right? We have 1 over, and then we had an x plus 3 and an x minus 2. So those two factors would cancel with the ones in our LCD, but then not canceling, we'd be left with the x plus 5, and then also the x minus 4. So those are still part of the LCD, but not part of that second denominator, so they would not be canceled, and they would be left there standing. Really multiplied by the 1. You could put the 1 in front of those if you wanted to. You wouldn't really have to. It doesn't change anything. But we definitely have to keep that minus sign in between those two main terms there, as we've done. Okay, so let's keep going now. After the equal sign, same kind of thing. We're going to have that 3 that was in the original numerator there. The x minus 4 and the x plus 3 would cancel with those matching factors in our LCD, but then left not canceled would be the x plus 5 here from our LCD, and then also the x minus 2, because those were not represented in that denominator, therefore they wouldn't cancel. Okay, and so what we have here left standing is what we have after clearing the fractions. Well, as you can suspect, there's a lot of algebra to do still here. So let's keep going, and we'll start by multiplying all these binomial sets together. And to do so, in the first term, we keep the 4 out front. If I FOIL together the x plus 3 and the x minus 4, that will leave us with an x squared minus x minus 12 in parentheses. I'll close that up, then a minus sign. Same thing with the second set of binomials. We'll multiply those together, and that would give us an x squared plus x minus 20. Then our equal sign, and then after that we have our 3, and then foiling the binomials following it would give us a trinomial of x squared plus 3x minus 10. At this point, we would have to distribute everything that's in front of all these parentheses. So the 4 is getting distributed in the first set, the minus sign for the second set, and the 3 for that next set. So altogether, we'd have here 4x squared minus 4x minus 48, then a minus x squared minus x plus 20, and then equals, and then a 3x squared plus 9x minus a 30. Okay, we're getting there. We have to keep boiling this thing down. Combining like terms would be next. So notice on the left side we have a 4x squared and a negative x squared. We could combine those together to get a 3x squared. Then we have a minus 4x and a minus x. Put those together to get a minus 5x. And then we have a minus 48 and a plus 20. Together that would be a minus 28. That's all still on the left side of the equal sign. On the right side, we don't have any like terms to combine. We'll just copy it all down as 3x squared plus 9x minus 30. And now our goal, of course, is to work on getting x alone. And to do so, we'll start subtracting things through. Notice we have the same term for x squared on both sides. So if I were to subtract 3x squared from both sides of the equation, those would completely cancel out, leaving us with a negative 5x minus 28 equals a 9x minus 30. We'll borrow our variables first, smaller to larger strategy here. And to do so, I'll add 5x to both sides. That would leave us with a negative 28 equals a 14x minus a 30. And at that point, we could add 30 to both sides. That would give us a 2 equals 14x. And then we could divide by 14 to take this all the way to the finish line here. 14s would cancel. We'd be left with x equals 2/14, or you could just say 1/7. And we'd want to check this as well. To save a little time on the checking process for an uglier answer like this of 1/7, which of course could be done by hand with the arithmetic, but we're going to save a little time and use a calculator. I want to show you how to go through this process. So in the calculator, we're going to hit the y equals button in the top left corner, which will open up this equation editor. We've used this before with other topics. And we're going to put, for y1, the entire left side of this original equation. So we have to be very careful with this. With fractions, you have to use parentheses to contain multiple terms. So with the first term being 4 over this trinomial, I'm going to put 4 divided by, and then use a set of parentheses to contain the x squareds. We'll type in x squared and then plus 3x and then a minus 10. Then close the parentheses. So that's that first denominator, which now wraps up that first fraction. Then we're going to want to hit minus, which was between those two fractional terms. Then we want another fractional term where the numerator is 1. So we'll hit 1 divided by, and then another set of parentheses to contain that original denominator, which was, of course, x squared plus x minus 6. We're just typing this all in our equation editor. Now, that's the entire left side of our original equation. which is all I want to put in for y1. So we have that whole thing typed in there very carefully. Sometimes a typo can be very troublesome because it ruins the whole process, so be very careful on this. Okay, we're then going to go on to y2 and type in the right side of the equation, which was a single fractional term where the numerator was 3. And then we're dividing by the entire denominator, again in parentheses. It was x squared, and then minus x, and then minus 12. Close up the parentheses. That's that right side. Now, the whole point is for us to check the answer of 1/7, and as we mentioned earlier, we would want the left side and the right side to be equal, and furthermore, we don't want any division by 0. Now, the good news is that a calculator will have a fit if it's trying to divide by 0 and give you an error. So we should be able to tell if that's happening, but we should also be able to tell if the left and right sides are equal by looking at our table of values for the left and right sides being in y1 and y2. So to look at the table, we're going to hit second graph, but before we get there, we're going to set up the table a little bit. So I'm going to hit second and then the window key. So if you're looking at your TI calculator, the window key has an option for you to set up the table. And so we're going to go down to table start is fine, but instead of for independent, that option, we're going to go to ask instead of auto. So let's flip over to ask and then hit enter, and that will set up the table. So now when I hit second and then graph, which will give me the table, notice the table is completely blank, including the x values, which it's waiting to hear from us on. So it says x equals at the bottom. This is where we want to type in the answer we got with our algebra here of 1/7. So I'm going to type in 1 divided by 7. That's our answer of 1/7. Now, when I hit enter, we should expect to see, if this is a true solution, we should expect to see the exact same output in y1 and y2 columns here, and including no errors. So let's hit enter, and sure enough, there it is. So it's estimating it as a, it's probably a fairly ugly fraction. It's giving us negative 0.2475, but notice it's the exact same for y1 and y2, which confirms to us that the left side and the right side of the original equation both match, and that there are no errors means we're not trying to divide by 0, which means 1/7 is our solution. Let's try one more problem in this topic here. This next one begins as 2 over x cubed minus 1 plus 4 over x minus 1 in parentheses times x squared plus x plus 1 in parentheses. Then we have plus, and then we have 1 over x squared plus x plus 1. Now, notice in this problem, I'm putting this one in here on purpose to help you understand you have to pay attention to the details of how a problem begins. Notice we're not given any specific instructions, and truthfully, if it was in a textbook or something, you might have a little set of instructions telling you to solve or simplify or something. But I purposely even left those off because I want to draw your attention to the fact that this original problem here is not an equation. So let's just make an observation. This is not an equation. How do we know that? Because there is no equal sign involved. Notice there are a couple plus signs, but no equal sign. I purposely threw this one in here after having seen several examples which were all originally equations and yet looked similar to this. They had a bunch of fractional or rational terms, yet this one is not an equation. The reason that's a big deal is because that means we're not going to solve this, which means we're not even going to clear the fractions. So let me make a big deal here with some extra instructions here. We're going to simplify, not solve, which means we cannot clear fractions. Cannot clear fractions. That's probably the number one mistake made in a topic like this, where it's truthfully sometimes if you're working on a whole bunch of problems at once, confusing to know, am I clearing the fractions or not? And it becomes such a habit to clear the fractions that often it's misapplied in a scenario like this. So since we cannot clear the fractions, what are we going to do? Well, we're simply combining these fractions by getting a common denominator. So we're still going to do the whole LCD thing, but what we do with that LCD is what matters. So we have to go back and factor. The first denominator was x cubed minus 1. Of course, that's a difference of 2 cubes. We know that by now in factoring. That's going to be x minus 1 times x squared plus x plus 1. So we factored that. Nothing else can be factored. If you try it, notice that second trinomial in that second denominator, x squared plus x plus 1. You could try factoring, it's not going to work. Notice it also matches even that last denominator. Notice those all match the factor we now have in the first denominator after factoring it. So what's our LCD after seeing all of these factored forms? Well, it's simply x minus 1 times x squared plus x plus 1. And we're going to use that to combine these terms, which, by the way, as you may recall, means we're going to rewrite each fraction starting over with the LCD as the denominator of each fraction. So we have x minus 1 in parentheses times x squared plus x plus 1 in parentheses being written here as each denominator in our new fractions. We have 3 of them because that's how many we had originally. But then, as you may recall from this topic of adding and subtracting rational expressions, you have to go back through and possibly adjust if the original denominators were different. Well, you'll notice the first 2 denominators originally actually matched the LCD, so we can just copy their numerators down as they were. So there was a 2 in the first numerator and a 4 in the second. We just copy those down. But notice the third denominator was not the same. This is where we'd have to adjust by multiplying by what it was missing. That original denominator was missing the x minus 1 factor, which means we'd have to multiply its numerator by that missing factor as well, which means that new numerator is going to be an x minus 1. Now, there originally was a 1 there. You could put that in, but it doesn't really affect anything, so we don't even have to write that 1 being multiplied by this new numerator. Then we'll go ahead and simplify by adding like terms across the numerators now that we have an LCD. So 2 plus 4 minus 1 altogether, of course, is 5 plus, and then we have a single x term. So we really just have 5 plus x over x minus 1 times x squared plus x plus 1 as our common denominator, and that's where we end. So this is a simplify problem, not a solve problem, and I just wanted to make sure and contrast it with the solve equations we've been doing in this topic, because it's easy to get mixed up, especially if they're all, together on a test, which is typically the case. It's easy to keep clearing fractions, then all of a sudden forget that you cannot clear the fractions with an expression you're simply combining.